Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leader series, Concrete Sleeper Retaining Walls. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders, past, present and emerging. Before we get started today, I would like to acknowledge that today's webinar has been hosted with Engineers Australia's industry partner, Austral Masonry. Austral Masonry is one of Australia's largest manufacturers of concrete masonry blocks, retaining walls, pavers and stone products. Its commercial solutions include coloured and standard masonry blocks, large-scale segmental block retaining wall products, as well as a range of hard stand solutions such as commercial and permeable segmental block paving. Today we'll hear from our industry expert, followed by a live audience Q&A, and I encourage you all to send your questions through to our speaker via the chat box. I would now like to welcome our speaker, Angus Maley. Angus currently works for Protest Engineering as a senior structural engineer specialising in retaining walls. Before working at Protest Engineering, he worked at Retaining Solutions for 17 years, originally as a project manager, then moved into construction manager and finally ended up as their design manager. He has designed more than 100,000 square metres of retaining walls and project managed over 400,000 square metres of retaining wall projects. So please join me in welcoming Angus Maley.
Thank you for the introduction, Megan, and thank you for the opportunity to deliver a presentation on the principles and application of engineering large-scale concrete sleeper retaining wall structures, including the challenges and designs. In this presentation, I will discuss the fundamentals of retaining wall structures, their applications, challenges in designing them, and the latest innovations to reduce costs. A concrete sleeper wall consists of an upright post, most commonly a galvanised universal column or a universal beam, cast into a bored pier with concrete wailers or sleepers installed horizontally behind the upright piers. A drainage system is installed behind the concrete sleepers, generally consisting of free-draining aggregate, with geofabric used to separate it from the retained material, and a 100mm ag pipe at the base of the wall to direct water away from the wall, ideally into a stormwater system. Posts are generally installed at either 1.6 or 2 metre centres. Common post sizes used in the industry are 100 UC15, 150 UC23s, 150 UC30s, and 250 UB26s. Sleepers are generally 75 or 80mm thick and either 100 or 200mm in height. The system retains earth up to a height of around 3 metres quite efficiently. The system can be used to retain heights of a little over 4 metres, however expense and risk does go up. I have been involved with construction of a sleeper wall up to a retained height of 6 metres in an industrial setting. However, the retained and founding material was extremely good and dead men were used to add additional resistance. Projects like that are not very common, and I would suggest the use of other wall types when retained heights in excess of 3.5 metres are required, unless there is some early contractor involvement at the conception of the project. A basic history. Concrete sleeper walls gained traction in the civil sector in the 1990s, primarily in southeast Queensland, and started with precast concrete posts instead of the commonly used galvanised steel posts that are used today. These walls worked fine, however the concrete posts did create a larger footprint and also create some limitations to the system. I will elaborate more on these limitations later. The system gained popularity due to its small footprint, durability, and speed of installation. In the infancy of the system, these walls were primarily used to retain wall heights of up to 2 metres. The system works best when retaining and founding a stiff clay or better material, in cut, or if used in fill, where the embankment can be overfilled and cut back. Advantages of concrete sleeper walls. Concrete sleeper walls have the smallest footprint out of all types of retaining walls, which is one of the driving factors as to why they have become so common in the civil and building industry. They are generally cost effective. Like most other retaining walls, as the retained heights increase, so do their costs. Boulder walls tend to be cheaper than sleeper walls, however more land is lost, so when space is at a premium, sleeper walls tend to be the preferred option. Concrete sleeper walls are also a preferred choice due to their durability, especially when compared to a timber sleeper wall. A core fill blockwork wall, dry stack masonry wall, or even a boulder wall, however, will have greater design life provided they are maintained properly throughout their lifespan. In terms of construction, they are much quicker when compared to a core fill blockwork wall. When compared to a dry stack masonry wall or a boulder wall, they are similar in terms of installation speed. They work best in either a cut environment or when a fill embankment can be overfilled and then cut back. This has made them popular with civil contractors as they can prepare the retaining wall work zones with their big machinery and then hand over to the sleeper wall contractor who completes the rest. The speed of construction reduces the amount of time the cut embankment is left open, which reduces the risk of embankment failure and also means compaction is generally not required behind the wall. They are a low maintenance wall. Once they are installed, there isn't much to do in terms of maintenance, and due to the concrete face, there isn't anywhere for vermin to take up residence or spaces for weeds to grow out of the face, as is possible with crib walls or boulder walls. Now that galvanised universal beams or columns are used as the uprights, the system has become quite versatile. When precast concrete piers were used, it was easy enough to design the wall if founding conditions weren't favourable, either due to services, sloping toes, or poor foundation material, by simply extending board piers. It was, however, difficult to use this system when the wall needed to be designed in an environment that was outside the normal loading conditions of a live load of 5 kPa, a horizontal surface behind the wall, and in a stiff clay environment or better. Now that the system is using universal columns and beams as the upright posts, when there are higher loads above the wall due to either higher live loads or sloping grounds, it is just a matter of increasing the size of the UCs or UBs, increasing the board pier diameter, decreasing the sleeper spacing, and increasing the number or thickness of concrete sleepers. The ability to either bolt or have a fence connection welded onto the steel post is a huge advantage in terms of overall footprint and overall project cost. The fence connection means the fencing contractor does not need to auger and install a fence footing. Before the fence connection came in to the market, the options were fencing contractors would auger behind the finished wall, which ran the risk of compromising the geofabric that encapsulates the drainage aggregates, or void formers needing to be installed during the sleeper wall installation, which proved expensive and also relied on some degree of compaction around these void formers. Cost savings. The sleeper wall market is extremely competitive, and there have been numerous attempts to reduce the cost of the overall delivery per square metre of wall. There are a few that have stuck and I believe work fine. There are also a number that, while still employed by certain designers and contractors, involve a degree of additional risk. All of the cost savings I will talk about involve some amount of additional risk to the end product delivered. I'm not saying these cost savings should not be used, however, the risk needs to be understood by all parties and managed accordingly. The main cost savings are imported UCs or UBs, welded reinforcement to the base of the galvanised steel pier, thicker sleeper panels, smaller board piers, or use of smaller steel sections. First on the cost saving list is importing of the galvanised steel UCs or UBs. Everyone in the market does this. The cost of the steel post represents a large proportion of the overall delivery cost, so you simply can't play in this market if you aren't importing steel posts. Even if a concrete sleeper wall supplier was purchasing steel locally, a lot of this steel would have been imported anyway. Provided adequate QA has been conducted on the imported beams, this isn't an issue. Simply requesting mill and galvanising certificates from the importer is probably not enough. A rigorous QA system, including some third-party testing of beams after they have arrived in Australia on each delivery, should be occurring. I'm not confident this is happening industry-wide, however, this is based on my opinion only and can be taken however you want. Welding of reinforcement to the base of UCs or UBs. This approach is commonly used by a lot of sleeper wall suppliers and installers. There are a handful of people in the industry who don't like this approach for various reasons. However, from my experience, I haven't had too many issues with walls designed and constructed this way. It is hard to estimate, but there must be well over 1 million square metres of wall installed with posts using this base detail. Things to watch out for are the base connection design, the weld quality, and also the weld process. The welding process needs to ensure the bars aren't overheated. If this can't be controlled, the designer needs to design for reduced tensile capacity for the reinforcement. Sleeper design. 75 or 80 millimetre thick sleepers are the common sleeper thicknesses provided by sleeper manufacturers. Cover varies from 25 to 30 millimetres and concrete strength varies from 40 to 50 MPa. All manufacturers cast their sleepers in steel forms and use intense compaction, so table 4.10.3.3 in AS3600 can be used when calculating durability. Any structural engineer familiar with concrete design will understand that these sleepers are extremely thin and also slender when spanning 2 metres. On paper, a sleeper that is 75 millimetres thick, cast with 40 MPa concrete and 2 N10s will actually have more capacity than the same sleeper cast with 2 N12s, because once N12s are used, it becomes over-reinforced and the code penalises the design. In practice, the sleepers obviously aren't as strong. I believe this quirk in the code means there are certain manufacturers using this to provide a better sleeper design on paper, however one that will deflect more and is more susceptible to cracking. Another point to note is these sleepers are designed for where it will be installed long term. The sleepers, however, need to be demolded after being cast, moved to the holding yard, loaded onto a truck via forklift, transported to site, unloaded on site, then moved around on site with either an excavator or skid steer before being lifted into the wall. Plenty of opportunity for them to crack. When the wall gets to a certain height, around 1.6 to 1.8 metres high in a normal environment, a 75 or 80 mil thick sleeper, depending on concrete strength, reinforcement used and site conditions, starts to fail at the base of the wall. One option is to double up the sleepers at the base of the wall. Manufacturers are now offering thicker sleepers to handle the additional loading on higher walls or walls with additional loading. Obviously, installing 1 by 100 mil thick sleeper is a lot cheaper than installing 2 by 75 or 80 mil thick sleepers. Board pier diameters. In terms of design, the designer gets much more bang for their buck by using deeper piers than larger diameter piers. Concrete volume is a squared function of the diameter of the board pier. Concrete and the board piers represent a large percentage of the overall installation cost of the sleeper wall system, so anything that can be done to reduce the cost of the concrete is worth investigating. The issue with reducing board pier diameters is twofold: reduced capacity of the board pier and also construction tolerances. Just because something fits on paper does not mean it will work in the field. I've project managed countless projects using a 100 UC15 installed in a 350mm board pier. They work and they do save money. They certainly are not preferred by the install crew. On paper, it would seem there is enough room for the pier. However, if you break the steps from set out to pier install, it isn't hard for the holes to creep 50mm or more despite good practice. Firstly, the holes are set out with 1 or 2 people with a tape measure. I've never seen a level used when this occurs, so the tape measure may be on a slight grade, introducing the first potential for set out creep. The hole is then marked with line marking paint, which represents another 30 to 40mm of potential error. The process of a machine operator augering the hole, even if spotted, isn't the same as a hole being drilled in timber or steel that has been hole punched to center the drill. There will be a deviation from the board pier compared to what was set out, no matter how good the person who sets the wall out and how good the operator is. My preference is to use a minimum of a 450mm board pier for post sizes of 100 UC15, the 150 UC series and 200 UB series. Once the steel piers get to 250 UB or 310 UB series, the board piers should be increased to a 600mm diameter. As stated above, a 350mm board pier can work. However, this does introduce risks into the execution of these walls, and it is really up to the designer and installation company about how this risk is dealt with. I've heard of companies using 300mm diameter board piers with 150 UCs in a foundation that consisted of rock. Speaking to the head contractor at the time, this didn't end well. 150 UB14s. 150 UB14 weighs slightly less than the 100 UC15, but has a better moment capacity. What it makes up for in terms of moment capacity, it loses in flange width. A 100 UC15 only has a flange width of 99 mm. When you factor in construction tolerances, as mentioned above, and also the addition of a fence connection, there isn't much room for error in these beams. A 150 UB14 has a front flange of 75 mm. They are being used in the industry, and as you can see from my slide, these beams don't leave much room for error at all. I won't design a wall using a 150 UB14. However, I must note I have inspected walls that have been constructed using these posts, and the install teams have done an amazing job to get good bearing of the sleepers onto these posts. If you choose to design or install walls using these posts, you need to be aware of these risks and manage them accordingly. Risk and mitigation. Concrete sleeper walls from the casual observer is just an extension of a timber sleeper wall they have commonly seen. As such, they should be fairly easy to design and construct, and the fact that the contractors are now using steel posts and concrete sleepers should make them almost foolproof, right? Unfortunately, this is not the case. In terms of design, they aren't so straightforward. Earth loads onto the above ground structure, e.g. the sleeper and steel posts, is fairly straightforward to calculate using fundamental soil mechanics. The issue with soil mechanics, though, is that if you had 12 geotechnical engineers in a room and asked them a question, you'd probably get 13 different responses. The main difference with regards to loads onto the concrete sleeper walls come down to the use of C- or drain cohesion. The consensus is to use a C- of 0 in the retain material and use a small amount, if any, in the foundation material. My advice to any designer is to tread very carefully if you choose to use C- in your design. In terms of resisting the earth pressures, the system's restoring force is a laterally loaded board pier. Common design methods for the design of the board piers are Brom's, Rintz-Hansen, or the equilibrium method, to name a few. While all walls need to be designed with some sort of geotechnical input, the higher the wall gets, the more important this is. As a designer, this can be one of the hardest things to get. Quite often, after I've been engaged to design a sleeper wall and I request a geotechnical report that has been conducted on the site, I'll be lucky if I receive one. Sometimes I receive a clear and concise report that contains the information I require. This, however, does not always happen. The geotechnical report may be an acid sulfate investigation or perhaps a bedrock investigation. From the client's perspective, they have ticked the box and provided me everything I need to complete the design for the 2 to 3 metre or potentially even higher sleeper wall they need designed. So what's the problem? These reports quite often do not give enough information for the designer to complete their design. 2 boreholes are required in every house lot to enable the structural engineer to design the foundation of someone's house, yet the industry seems to think it is acceptable for retaining walls to be designed with limited investigation and substandard reporting. To be clear, what I describe as substandard reporting is not necessarily a dig at the geotechnical company that has been engaged to provide the report. If they have been commissioned to conduct an investigation into, say, the presence of acid sulfate affected soils, and the report has addressed that, then they have completed their brief. The fundamental issue is caused by they have not been given a good brief of what is required on the project. The geotechnical consultant does their job, the client thinks they have a geotechnical report, and now wonders why the retaining wall designer wants more. If you're specifying retaining walls on your project as a civil designer, it is up to you to guide your clients that decent geotechnical investigation is required before tendering and design can occur. It is a small cost in the overall picture of the job, but it reduces risks for everyone involved. It is easy to write, design and construct by others on your drawings, but if things do go south, you will be involved one way or another. Even if your PI isn't compromised, you will be dragged into it. I can't emphasize enough how important a good geotechnical investigation is for a project that contains large sleeper walls. Information required to design a retaining wall is as follows. Retaining wall parameters consisting of drain friction angle, drain cohesion, undrained cohesion, and bulk unit density. These should be provided in the body of the report. The boreholes also need to be conducted in the location of the walls for obvious reasons. Groundwater levels, if present, also is required. Depth of boreholes is also important to define the retained and founding material. If the wall heights on the job are 3 metres and the borehole has terminated 1.5 metres from the top of the wall, and we don't even have the full retained material defined, let alone the foundation material. Here is an example of a borehole that does not contain sufficient information. The borehole has terminated in the fill, so we don't know the depth to natural. There is no indication of strength of the material. Is the clay soft, firm, stiff? We don't know. There are no DCPs provided, and for this example, the report does not contain any guidance on what retaining wall parameters to use. When information is presented like this, it is very hard to design a retaining wall. Example of a good geotechnical report. This borehole has good descriptions of the various materials present in the borehole, including the strength of each material. DCPs have been conducted. The borehole has been drilled to sufficient depth, and the retaining wall design parameters were provided in the body of the report. This is the sort of information that should be provided to a retaining wall designer to enable them to complete their design. What is happening over the boundary? Sleeper walls, or any retaining walls for that matter, when designed into a project, are quite often on the boundary of the site. What is happening on the other side of the boundary is quite often not defined on the drawings prepared by the civil designers. Some civil designers do, and I take my hat off to them. However, on the whole, it seems the project inside the boundaries of the site is what matters most. Obviously, this is not the case if you are tasked to design said retaining walls. Near maps is pretty handy, however, nothing compares to going to site and walking the boundary. I highly recommend everyone who is designing retaining walls to visit the site on their project and check out the site as well as what is happening over the boundary. If there are pools, existing retaining walls, structures, or batter slopes that aren't shown on the drawings, then you need to design accordingly. If you design the odd retaining wall here and there, you may be able to get away without visiting the site and never have any issues. It's all a numbers game. If you design multiple retaining walls, at some point in time, there will be something on the other side of the boundary that you didn't design for. I would not rely on the contractor involved to pick this up for you. If you are the engineer conducting the inspections to provide the construction certificate and you only pick this up during construction, this is not a position you want to find yourself in. Alternatively, if you are only providing the design and someone else is completing the on-site inspections, you run the risk of them not picking this up. Site issues. Sleeper walls on a civil site are exposed to various risks throughout the civil construction phase. The civil contractor who has possession of the site and is responsible for the erosion and sediment controls on the site does not always consider the concrete sleeper walls on the job. Every now and again, a contractor will inadvertently direct the site's water towards a sleeper wall that is under construction. Generally, the highest loading from water will occur during the civil construction stage due to the fact that there are no structures with roof water systems connected. Normally, this is fine. If, however, a torrent of water is directed to the rear of a sleeper wall, it generally isn't going to handle this very well. While this is hard to manage from a wall designer's or installer's point of view, it is worth looking out for. Overloading a plant behind the wall is also another risk that is hard to manage when you aren't in control of the plant behind your wall. The risk, however, is quite real, and it's one of the leading causes of issues with sleeper walls during the civil construction phase. Sleeper walls located on boundaries where the site needs to be filled represents one of the largest site risks for this type of wall. As mentioned before, these walls are best suited for overfilling an embankment and then cutting it back before installing the wall. This process ensures good compaction of the retained material. The problem with large walls on boundaries is this quite often is not possible. If there are existing houses on the lower property, the contractor may not be able to fill and compact more than 1/2 metre or so before cutting back for the sleeper wall. The issue then becomes filling and compacting the site material after the wall is installed. It is very easy to install the wall and place the fill without compacting it. However, this will result in much larger forces on the retaining wall and long-term settlement issues. Compacting behind the wall needs to be completed with handheld equipment and closely monitored to make sure the material is compacted adequately, as well as the wall not being overloaded. Design considerations. If groundwater is present, this needs to be designed for. While groundwater is a design issue, it is also an issue for the installation team. In sands, this proves extremely difficult. If groundwater is present and the foundations are sand, alternative walls should be considered. Slopes above or in front of walls, when these are present, a global stability assessment is recommended. Deflection of steel post should be checked by the wall designer. This is especially important for higher sleeper walls. Tiered walls are quite common due to councils having height limits for a single lift retaining wall. The design approach seems to have changed over time, with the consensus being to design the rear wall with much deeper footings. I've seen designs where the front wall has been designed to handle the loading of the upper terrace wall. Fundamentally, this seems okay. However, in order to transfer the loading onto the bottom wall, a no-fines concrete backfill for the front wall is required. Whatever design approach the designer chooses, careful consideration of the interaction between the front and rear wall needs to be considered. This concludes my presentation.
Thanks, Angus. Well, now it's time for you, our audience, to get involved. So if you have any questions for Angus, please enter those questions via the chat box. And I also want to say thank you to everyone who submitted questions while registering for tonight's webinar. So what we might do is kick off with some of those questions. So Angus, the first question that I have has come from Victor Lorena, and his question is, can you please also discuss maintenance and reconstruction of parts of the walls, please?
Yeah, no problem at all. The maintenance on sleeper walls, as discussed in the seminar, isn't generally high. I mean, you'd want to be looking for any issues with your galvanising, and it's just basically maintaining the clay cap on top. In terms of reconstruction of the walls, you generally don't want to. Well, generally, if there's an issue, it's quite often a post that's failed. If a post failed, you don't want to be pulling them out. It's a case of pulling the sleepers out, drilling a post either side, cutting down the failed post, and reinstalling the wall. If it's a sleeper that's failed, it's just a simple matter of pulling it out and replacing. Mightn't necessarily be so simple when you've got limited access, but they're generally the two things that fail on the wall. You generally want to be getting machinery in there to do it.
Cool. Thank you. There's a heap of questions which are here, so we'll get through all these. The next questions come from John Romanos. So thank you, John. And his question is, what is the maximum height of the wall which can be constructed?
I have talked about this during the presentation, but I would like to go over it again. Sort of around the 3 to 3.5 metres is where you're wanting to tap these walls out. They will go higher, but your risks really increase. Generally, the projects that don't have good geotech information on them, and you run the risk of hitting water or bad ground, and you're usually too far down the track to be doing something about it. So if the walls can sort of max out at about 3.5 metres, I think it's going to be better for everyone involved long term.
Awesome, thank you. Another question's come through. You may have touched on it, but how do you select the type of retaining wall and the considerations?
Selecting the type of retaining wall, it really comes down to it's horses for courses. You've got to work out what the budget constraints are, what the footprint required is going to be, what your ground conditions are, what the maximum height is. There's no real rule of thumb. As stated in the presentation, sleeper walls are great for good ground conditions, not too much going on, up to about 3 metres. Anything above that, you're going to want to think about doing something else. No real hard and fast way. You've just got to take all factors into consideration.
Well, probably then runs into the next question from Mark Morelli. And this one was around, what are the limitations of concrete sleeper retaining walls?
They don't like being in locations where you've got they're hard to install when you've got groundwater involved, as well as the design of it. They're extremely hard to install when you've got groundwater and a sand foundation. Even though they're still getting designed into these places because people are more worried about the footprint. They're not great in water environments, although again they are getting spec'd more and more into basins. And I mean, really, the main limitations is probably that height, and that 3 to 3.5 meters is for a live load of 5 kPa. So just because it works on a house lot doesn't mean you can then spec a 3.5 meter high wall and want to put a 20 kPa live load in an industrial setting and think you're going to still get a good result. So yeah, mainly the height and ground conditions that are probably the biggest limiting factors.
Cool, thank you. Excuse me. I've got the next questions come through from Raymond Tan, and Raymond's in New South Wales. So thank you, Raymond, for this question. And it is, how does this compare to conventional block work with concrete footing in terms of construction cost and construction duration? And then he's got limit the wall height to 2.5 meters high and no issues with ground condition.
So for those height ranges and for good ground conditions, as has been said, on a civil site, there's no comparison. Sleeper walls will hands down win every day of the week. Even in a building setting, like even on house construction, there's been a big swing to the market for these to be installed by the even self-performed by like a home builder, and almost certainly they're gonna win in terms of cost. Where you mightn't do it is if, let's say, you had a house that had a hell of a lot of blockwork wall, and your and your builder was really good at building blockwork wall. He's probably not going to go and get a machine in to do a small quantity of sleeper walls. But as a rule, they are definitely better in construction costs. In terms of construction duration, again, hands down, they'll beat a block. There's the time that you need to let your concrete cure. You know, you're not waiting 7 days for your blockwork wall to cure before you can load it. You don't have a big void behind it. Much quicker and a much cheaper option for those wall heights, for sure.
Awesome, cool, thank you, excellent answer. Scott McPherson from Queensland has sent through a question, and this one is, do you think the adoption of the 1 metre restriction prior to requiring an engineer is too conservative? I note that New Zealand allows up to 1.5 metres for timber walls, however.
I think it's a good question. I honestly don't think that's too conservative. There's been times when I was on the contractor side where we'd be asking developers, when we'd be putting prices in for walls that were 600 and 800 high, and they were defaulting to wanting them engineered. I think it's a good approach. I've seen a 600 high wall built by someone, and I'm not sure what ended up happening with it, but it potentially had a couple of $100,000 bill that was going to go with it because it wasn't performing as it should have. House lots, new housing lots are probably 400 square meters. There's no real room to get a machine in to try and fix these things. So if you've got a 1,200 high wall in your backyard, in your mum and dad's backyard, who have got no idea about, you know, the industry, and it starts failing, they're left with a potential hand grenade down down the track. So I think the 1 metre is fine. I think it's going to save a lot of headaches moving forward. Even though it's a little, I do understand your point, but I think long term for our the community, I think it's the right thing to do.
Awesome, thank you. Another question's come through from Sagar. He's also based here in Queensland. Recently, there are several manufacturers who are using welded reinforcement to steel posts without shear legs. Comments on using the welded bars overall, and also on missing shear legs. Is that legs or lips? I'm not quite sure.
Yeah, legs.
Sorry,
legs. You're right. You're right. Yeah. So good question, but I think a lot of the times when people are specifying shear legs, they're more of especially for the lower height walls, they're more just to locate those bars, to keep the bars straight. that is one of the issues with the steel post with Rio welded on. It's all good on paper, but they don't always stay straight by the time they've been bundled, like galvanized, strapped up, and then and shipped. And it does make it hard for the installer to get them in place. With the old AS3600, which had a different approach to shear, you could get these walls to work without shear leagues, I think up to about 2.4 meters, and then you'd need shear leagues. With the new code, with the new revision of how we calculate shear now, I think it lets you get a little bit further. So for the high walls, you're going to need shear leagues for sure, but I think it's more, those shear leagues are more for positioning, which I do think is an important thing, at least for positioning of the bars, even if it's not for the actual overall shear capacity.
Excellent, cool, thank you. Another question's come through, a lot of questions coming through from Queensland. Angus has asked, has earth reinforcement, in brackets geogrids, been considered in the design of sleeper retaining walls?
I have considered it on a few hairy jobs. I don't think I've designed or constructed one that has had it involved. One of your issues is how you actually connect it to the face. I mean, you could potentially wrap it around your sleeper, but I don't think anyone's going to be real happy about that. And also you've got your UV in it, and it potentially won't be UV stabilized. So yeah, it might be able to be used on certain jobs that you've got a real problem with. But it's got its issue, and connections are probably your biggest issue. Your other issue is, like, generally when geogrid is used, you're compacting behind a big masonry block with gravel infill, and they're a lot tougher for your hand compaction equipment than, say, a 200 mil sleeper. So I think there's a potential of having problems of cracking sleepers when you're focusing on that hand compaction zone, which is critical for those geogrid structures to perform well. So yeah, I think it's one to think about, but yeah, haven't seen it used as yet.
Well, thank you. I've got a question here. Can we do a concrete sleeper retaining wall on a sandy or a rocky site?
So on a sandy site, if the sand holds together, if it's a nice dense sand and holds together, and then there's no water, they're not too bad, provided you're filling those holes quickly. If you're getting a really fine single grade sort of sand, it can become problematic. And as mentioned before, if you're getting sand with water in your foundations, it becomes extremely difficult. Best way to do it would be a continuous flight auger, but not many people in the civil sleeper game have access to them. Another option is using former tubes, which can be done, but it comes with risk. So yeah, it can be done, but your risk goes up. Rocky sites, the sleeper industry is getting good at drilling rock because they've had to. So yeah, rocky sites. I've been involved in a lot of projects with some extremely high strength rock. Sites that I would have said 10 years ago wasn't suitable for sleeper walls. But unfortunately, the industry's just got better. They're throwing bigger and bigger machines at it. They're throwing better augers at it. And so it can be done. Obviously, there will be an expense on it. But yeah, it can be done, and it is commonly getting done at the moment with some really high strength rock.
Awesome. Thank you. Thanks for that. Next question's come through from Timothy, and his question, how important is the surface drain at the top of the wall versus letting the water go over?
Surface drainage on top of the wall is always very important. It's like the egg pipe. So quite often, the connection of the egg pipe down the bottom, it's quite often overlooked. On a house lot, when you don't have a massive catchment behind it, probably not going to matter so much if it's overlooked. If you've got a big catchment behind it, it definitely should be getting picked up in a surface drain and taken elsewhere. If it's allowed to go over the wall, it's not great for your clay plug, and it's also not great for your foundations having water ponding in your foundations. So really, like sort of everything, it's sort of horses for courses. But yeah, with a big catchment behind it, I would say it's extremely important to have a surface drain that's adequately performing rather than letting it tip over the edge.
Awesome, thank you. A lot of questions on maintenance and durability. And the next one, how is long-term durability and serviceability calculated for concrete sleepers supporting housing and any other infrastructure? And he just ends that question with, how is construction quality guaranteed, as I see so many sleeper walls losing backfill due to incorrect construction methods?
Okay, so the long-term durability is first of all, it's the durability of the concrete sleepers is picked up with AS 3600, which is a function of exposure classification, cover, and concrete strength. Your galvanizing, you've just got to go to your various galvanizing codes, which certainly aren't as helpful as 3600, but they do give reasonable advice as to work out your durability. And most sleeper designers are sort of aiming and most for that sort of 60-year design life, which is mentioned in AS 4678. The last question was, how is construction quality guaranteed? That is a good question, and it's one that I don't think is policed enough in the industry. There's a lot. Well, I believe there's a lot of these walls are getting signed off by RPQ engineers that are receiving photos during construction. Photos are good, but the installer's only going to send you photos of good stuff. He's not going to take a photo of the bad stuff and send it to you. So in terms of answering that question, I think it needs some good on-site presence of the certifying engineer. Ideally, you'd have a decent project management team as well with the installers, but I'm not sure how often that's happening in the industry either. So, I mean, yeah, it comes down to on-site presence, lots of photos, but photos on their own is not enough to guarantee that things are getting constructed as you would like them to be.
Fair enough. Thank you. Okay, so some of the questions that have come through live today, so a huge thank you. I've just been seeing them come through. And I think we have picked up some of those through some of these questions that we've gone through. But we've got a question here from Mulligeta. So their question is, how is the effectiveness of this to release retained water compared to the standard retaining walls with weep holes?
I think that question's referring to the ag pipe. It's a good question. The ag pipe's quite often overlooked and it's quite often buried by the civil contractor, which is not ideal. And then I haven't seen any walls fail from it, but they do tend to get pretty mushy down the bottom, and you end up getting phone calls back because you've got a homeowner that's not happy with why his backyard's all soggy. The issue with weep holes on a sleeper wall, which sometimes it's the only way to do them, you can install a horizontal weep hole, is where that water goes. The ideal, and then if your tile wall's not grading away, or it's just into someone's backyard, which has just got lawn and topsoil, it can get quite soggy there. So it's not the best approach on sleepers. The best approach is that ag pipe getting connected into the stormwater or roof water system of the homeowners. But it's one of those really overlooked things, and there's been countless civil contractors that have buried these things because they just do. I think they look ugly, even though they're a quite important part of the wall.
Thank you. We had a question which has come through from Linda. So thank you, Linda, for watching. And the question is, how do you consider global slope failure for the multiple narrow stepped retaining walls?
That's a good question. I think it's one. I think I had sleeper walls up on my slides about risk, but I never really talked about it. A global stability assessment should be done on tiered walls because it is a risk. they're hard enough to analyse the double and triple tiered walls as they are, and if they're not getting a global stability check on them, I think there's a real potential for a failure. It's ultimately, that's probably where the failure is going to happen on a lot of those structures. So if the structural engineer involved can't do it, it's just send it out to third-party geotech that can do a third-party check on it, just to make sure that case is covered.
Well, thank you. Now, you may have answered this question, but it's come through from Navid. What is the average lifespan comparing to wooden retaining walls?
So, I've talked about the 60-year design life, which is referenced in AS 4678, although I don't know how enforceable that is, because it is a typical application, but it is what we generally default to as an industry, and I think it's a good thing to be defaulting to. Timber sleep walls, I don't know exactly how long they last, but I would have thought by 8 they're looking pretty tired, and I think if they're getting past 15 with a treated pine sleep wall, you're doing pretty well. But that last comment is opinion, and if it's wrong, then it's just I'm just shooting from the hip on that. But there's timber sleep walls never going to get 30 or 40 years, not even going to come close to a concrete sleeper wall, provided the concrete sleeper wall has been built properly.
Yeah, and I'm thinking that and forgive me, I could be wrong here, but there was a question around galvanised posts in a coastal zone from a durability viewpoint. Are there any concerns?
Yeah, there is, because you've definitely got a worse exposure classification. So I don't think they should be specified too close to the to breaking surf, and you need to be careful there. I mean, if you're a couple hundred meters from the beach and you've got a galvanized concrete sleeper wall, your durability is almost certainly going to be compromised. I don't think that's a good spot for them to be in.
Thanks. Ashley sent through a question, so big thank you to Ashley. Do you provide a waterproof membrane immediately behind the sleepers, or let the water pressure release through the wall?
I will never specify a waterproof membrane behind a sleeper wall. They will. Well, firstly, going back to that ag pipe, you want the water to come out through your ag pipe. As also stated before, quite often these aren't connected. So I always like the fact that when they're getting designed or constructed, you know that even if the water builds up, it's got a release point through the wall. It's not ideal, but you've got a semi-fail-safe there. Putting a waterproof membrane up there, one, it's not really going to work anyway. It will help a bit in terms of getting water, stopping water coming through. And if you were to use one, you would definitely want to design for an elevated water pressure. But if you're in an environment where you're putting a waterproof membrane up, I think you're using the wrong wall. If you want things to be waterproof, you should be using a blockwork wall and waterproof it properly. Trying to waterproof a sleeper wall, they're just not made for it. There's too many areas where water can get through. So I definitely think it's the wrong wall type for it. And putting a waterproof membrane is just going to put more loads on your wall. So I don't think you're really gaining anything for it.
Cool. Thanks, Angus, for that one. I've got another question which has come through from Rashad, and so thank you for watching. And that question is, how do you work around wall footings where you have existing utilities running?
It's a good question. It's more of an installation issue. However, as a design, I'm sitting in the design seat now. It's something as a designer you need to think about as well. Each council or state will have, and also depending on what type of infrastructure, will have minimum distances they want you to be away from certain infrastructure. Like if you're going over an HV cable, you're almost certainly not going to stick a board pier in there, and you would use vacuum excavation just to get around it. A live sewer, depending on how big it is, depending on how confident you are, where you know where it is, you might use a board pier. maybe it'd have to be risk assessed. But I mean, when in doubt, you use a sucker truck vacuum excavation to get your piers down. On a civil site where they're not live, your risk assessment changes a little bit, because they certainly don't use vacuum excavation for every bridge over service. It's not 100% live on a civil site. But yeah, it just needs to be risk assessed. But yeah, the easiest way is get a sucker truck in, and then that way, yeah, your risk levels go down.
Awesome. Thank you. I've got a question, and I am feeling for you being the only person here that I'm so we might start to wrap up some of these questions shortly, but there's one here from Bass who said, you mentioned briefly, Angus, but I missed it. Can you please repeat what design theories or methods are used to determine the pier design, depth, diameter, etc.?
So some that are commonly used is Brom's, Brinch Hansen, and the equilibrium method. There's PY method, but I think that might have something to do with Brinch Hansen method. They're the ones that are generally used, but they're any laterally loaded board pier analysis is fine, really, because that's all they are.
There is a question which has come through, and I think we've got probably two more questions, Angus. You've done a brilliant job, and I'm sure everyone agrees with me. Does the sleeper wall typically need temporary propping during compaction of retained soil behind the wall?
No, not during compaction behind the wall, because if you propped your piers, you'd bow your sleepers. And to get a propping system that could prop your sleepers and your posts would be fairly considerable. So light compaction and carefully and thin layers is the best way to compact behind them. But as stated before, they're not the walls that are designed to be compacted behind. Obviously, there will be environments where this needs to happen, and it can be done, but light compaction, thin layers is what needs to be done. Unfortunately, most civil contractors don't know what light compaction equipment is, and most sleeper installers don't want to do the compaction. So you get left in this no man's land of no one really wants to do it properly.
Well, Angus, I've got the last question for you, which is kind of a few people have asked on something a bit similar. Really, they're asking, one, they're saying great talk, so congratulations, but is there any literature you can recommend for further reading on the different methods of pier resistance, deflection, and also any good programs for mass, gravity, block walls, etc.?
If there was some good literature, I would love to read it. It's a good question because they're a really hard wall to find all the information to design for. If you went to design a cantilever blockwork wall, you could go on the internet right now and you could find probably 7 worked examples quite easily. But with a sleep wall, you can't. So I understand the question, but yeah, I don't have the answer, unfortunately. You've sort of got to find a few different textbooks and put everything together and come up with something you're happy with.
Awesome. Well, look, that I think is all the time that we have for today. So please join me in once again thanking our speaker, Angus Maley, for his time and input this afternoon. I would also like to thank Engineers Australia's industry partner, Austral Masonry, for their support with today's webinar. So if I could please ask a quick favour, if you could complete the short feedback form, which is linked in the description box below. And if you do that, it really helps us improve and plan our future sessions for you. So finally, thank you again for joining us, and we hope to see you at our next Thought Leaders event.